A conventional drone is controlled by varying thrust on each one of its motors and propellers, and by increasing the thrust on one side of the drone, it will cause the drone to tilt. Now this works nice and well down here on Earth, where the atmosphere is nice and thick, but up in space, things like rockets and large satellites require a different form of control. Now, probably one of the most common forms of control for the larger rockets and satellites is gas thrusters. These work by expelling high pressure gas out of very small nozzles mounted at various points on the spacecraft. Now what I want to do is try and apply this gas thruster reaction control system to a drone. But first, let's talk to someone who might know a bit more about this subject than I do.
Hello.
Hello!
Hey, Tom. Oh, wow, that was really loud. How's it going, man?
Good, thanks, and you? This is Joe Barnard. He has a YouTube channel called bps.space, where he builds model rockets. But the rockets that he builds aren't your average model rockets. Yep, this is a replica of the SpaceX Falcon Heavy, and it uses thrust vectoring for control. Joe has been developing this thrust vectoring system to eventually land a model rocket propulsively. That's right, this video isn't being played in reverse. More recently, he's been experimenting with a gas thruster reaction control system. So I had to ask him a few questions. If you could split up the whole of an RCS project into 3 components, what would they be?
You want to start with the plumbing. That actually is pretty accurate. You probably want to start with the plumbing so you can figure out which valves you need to... Oh, actually, well, okay, the problem is it's all interdependent. If you start with the valves, you also want to consider the actual moment that you want to impart on the vehicle. If you want to do the math about it, you'll have to consider the flow rate in your valves. But mostly you'll start with the plumbing. Then I would focus on how are you going to control this? So like, what is your flight controller going to be, your power source, your wiring, and maybe a little bit of layout stuff. And then the last part of the project, which in my mind, or at least in my project, has taken the longest, is the control side of things. So what does the control logic look like? When does the computer decide to fire a valve? And how do you keep your vehicle from spinning out of control or not controlling itself at all?
And crashing.
And crashing, right? Yeah, like how do you minimize your thump factor?
So as Joe mentioned, it's best to get the hardware sorted first. This will include things like the pressure vessel, the valves for controlling the airflow, and also the nozzles for exhausting the high pressure gas. Now with Joe's system, he has to fit his into a model rocket, which means it has to be quite compact. Whereas on a drone, I have a bit more space to play with. So for my pressure vessel, I'm going to be using plastic bottles. This is a 2-litre plastic bottle, and it can handle upwards of 150 psi. It's really lightweight, and they're really cheap. Also, my compressor only goes up to about 116 psi, so these bottles are pretty ideal. In order to turn this plastic bottle from a drinks container into a pressure tank, I need to connect a sealed tube to the cap. This is done by 3D printing a heavy-duty threaded cap. Then an O-ring is inserted to keep a tight seal with the throat of the bottle. And after a quick pressure test, it seems to hold fine. Because the control of the drone is somewhat limited by how much air can be stored in the bottles, it's important to optimise the nozzles for the maximum thrust possible without wasting too much air. So I've built this thrust test stand. It's comprised of a load cell to measure the thruster nozzle, a set length of tubing, and the solenoid valve that will be used on the drone. The data from the load cell is then logged to an SD card using this Arduino board, so that I can plot a graph of the thrust later. The air is supplied from a single 2-litre plastic bottle, so I can get a rough idea in terms of thrust duration. It's then filled using this larger tank via a pressure regulator, so that all the tests are as consistent as possible. I chose to run the test at 60 psi pressure, as it would allow multiple tests to be run without filling the tank every time. Plus, I'm more interested in how it will perform at lower pressures, as that's when I'll lose control. To find the best nozzle design, I chose several options, none of which had any theoretical calculations behind their design, but that's the advantage of having a test rig. The first nozzle was a straight through nozzle, which would act as a control. The second was a straight cone nozzle. The third was what I'd call a conventional rocket nozzle with its distinct bell shape. And the fourth is the reverse, or a horn style nozzle. Each nozzle has the same throat diameter of 4mm, as well as the same exit diameter of 10mm, and a length of 15mm. Take a guess which nozzle you think will perform the best in the comments down below. I ran each thrust test 6 times per nozzle to get an average, and imported the data onto the following graph. Now, before I tell you which nozzle performed the best, let's just admire how little thrust this system actually produces. Yep, that's right. The best nozzle produced a peak thrust of 0.62 newtons, or the equivalent of lifting about 63 grams. So here's the lineup. Did you guess that the straight nozzle would perform the best? Also, the bell-shaped nozzle performed the worst out of all of them. Now, because these solenoid valves have a small orifice of about 2 to 3mm, I thought I should probably try a smaller diameter nozzle. So I made this 2mm diameter straight through nozzle. And it outperformed all the previous contenders in both peak thrust and duration. So I'm going to go with this. Let's talk about the drone design. So the plan is to use 2 counter-rotating propellers mounted inside of a single duct. This will be mounted in the centre of the drone and won't provide any pitch or roll control. It will be able to provide yaw control by adjusting the torque from each of the motors. Then for pitch and roll control, I'm going to have 3 nozzles mounted on 3 long arms extending out from the centre of mass. The reason for choosing 3 nozzles is because it's the minimum amount of points of thrust you need to have stable control. Similar to how you can't have a stool with less than 3 legs. Now, the reason why a regular drone will have 4 arms or more is because they need equal amounts of propellers to counteract the torque. But because these nozzles don't produce a torque in the yaw direction, I should be able to get away with 3. The frame parts consisted of a few 3D printed parts using PLA filament supplied from my filament sponsor, 3D Prints UK, as well as some aluminium spars. When assembled, it created a triangular frame around the centre duct. Then I mounted the electronics, starting with the relays that would apply power to the valves. Then the valves themselves, which one of them weirdly had a hole in the top which would leak air from. But the leak was very slow, so it shouldn't be an issue. Then came the flight controller, Arduino board and radio controlled receiver, which allowed me to actuate the valves from my controller. I then mounted the arms, which the nozzles would attach to, and temporarily mounted the nozzles using tape, in case they need to be removed later for modification. So now most of the hardware and electronics are complete, apart from mounting the bottles. But before I give it a test, we need to consider how the flight controller will control the valves. With a regular drone, the throttle can be increased or decreased at different rates depending on the required control output. But these valves can only be fully opened or fully closed. Therefore, we need to configure the system to know exactly when to trigger the valves, which is where, once again, we need to seek Joe's advice.
So this has been the constant theme of like all of the rocketry stuff I've done. It's actually comparatively easy to develop all the hardware and build everything, but the devil is in the software. So right now I have like if you were an actual controls engineer, you wouldn't want to hear this, but it's just a gated and saturation limited PID. It's fairly primitive. If you do enough simulation, so like I have a simulation built up for how the vehicle should actually be able to control itself and simulate. That helps you dial it in, but there are much better ways to do it if you're willing to get into like full state space control or something that actually considers the torque that each thruster can put out. But that's also kind of a nightmare. So it's easier to just set up on a test stand. Yeah. I don't know if we've covered this yet, but that's kind of how I've been doing it. You have basically, you can see actually 2 holes in the vehicle right around the center of mass here. And so it's actually slightly below the center of mass, so the vehicle wants to fall over. And what I've been doing is just setting it up in this mount where it can rotate on this axis and this axis. And you just start loading PID values and giving it a shot.
Just trial and error.
Yeah, that's not how it really works in the aerospace industry, but these are model rockets, so.
Gets the job done.
Yeah.
All right, well, I think that's enough information for now, hopefully.
Yeah.
I'll keep you posted on how this thing goes.
Good luck, man. Control systems are hard, but it seems promising.
Well, yeah, you're far better at control systems than me.
Well, thanks so much, Tom. Good luck.
Yeah, you too.
Yeah.
All right.
I'll talk to you soon.
Bye. Now I'm going to take a slightly easier route to Joe, as I want to use a conventional drone flight controller. This will save a lot of time, as the code in these things is far beyond my knowledge level. So to convert this flight controller into the similar gated PID system that Joe mentioned, I'm going to need the Arduino to run a small bit of code. Essentially, the flight controller will output a throttle value, as if it were communicating with a drone motor. The Arduino will read this signal and convert it to an on and off signal by gating it with a set threshold. When the output signal from the flight controller increases above this threshold, the Arduino will open the valve. Now, this threshold will depend on many different factors, so let's program it into the Arduino and give it a test. So I've hung the drone from the ceiling so that I can sort of simulate it in mid-air, so it can now swing forward and backwards. And as you can hear, the valves do actuate. Now, I can't test the roll in this configuration. I've just hung it roughly about the balance point for the pitch axis. And you can hear the valves actuating when I move the drone. So what I'm going to do is I'm going to pressurise the whole system using my large tank down here on the ground. And see if this works. It should work. All the valves are actuating. I just haven't tested it with the air yet. So I should be able to push down on here and this nozzle will fire. That's actually really well tuned already. Oh, I don't know what happened there. It's working. Let's try it the other way. So if I push this up, the two jets at the front should fire. So we'll try and hold a specific angle. Okay, it slowly gave up then. What I can do is I can also flick this switch and it will always try and self-level. It's trying to self-level. So, because it's hanging slightly nose forwards, as you can probably see, apologies, my remote keeps talking to me. Shh. Yeah, when it hangs nose forward, it will try and lift the nose to bring it level. If you watch, 3, 2, 1. That is working way better than I expected. Wow. Right. Oh my god, that is so cool. It sounds absolutely amazing. And level. Right, cool. Now I think we need to install the bottles for its own air supply and add some motors. The motors were mounted bottom to bottom and soldered in a way that they would rotate in opposite directions, so they provide a net zero torque. The bottles were then mounted to the frame using large zip ties, and then it was a case of plumbing all the bottles and valves together. This was done using flexible PVC hose that would push fit into various connectors, which makes the plumbing super easy and also reversible if something needs changing. I then hooked it up to the air tank for a pressure test and to check for leaks, which was successful. Okay, so the drone is all ready to test. I haven't pressurised it yet, but I've got all the electronics turned on. I'm actually going to run it on a tether. That way I can use the full volume of the large tank and I don't just run out of air really quickly. Because for this first test I want to just sort of gauge how it feels on the ground. So let's hook up the pressure tank and give it its first test. I'm slightly nervous about this, but you know, it's got to be tested. So let's arm the motors. Let's check the valves. Okay, all the valves are working. Right. Increase the thrust. Let's try that again. The motor and propeller I chose should be capable of 1.5 kilograms of thrust per motor, and this should be plenty to lift this drone, but for some reason it didn't want to lift off the ground. So I tried raising the duct off the ground a bit to see if it improved the airflow. It definitely needs the bit off the ground just to get the airflow.
Get the draft.
Yeah, I had control though. Yeah, it's controllable. These initial tests were ran at about 60 to 70 psi. The reason for this is when I fill the 24 litre tank to 100 psi, and then fill the 6 litres of bottles from that, the pressure drops to around 80 psi. Then, after messing around on the ground for a bit, the pressure drops some more. Okay, that seemed an issue with the tether. It seemed like it pulled on the drone. So it was time for the first untethered hover. For most of the following test flights, I was adjusting the values inside of the flight controller to make the drone react quicker and hopefully achieve a more stable hover.
Much better.
That was a lot better.
Much better. That's fantastic.
Yeah, the battery dies like instantly. I was full throttle there. Yeah, I think I need to get a better battery really.
Yeah.
With the newer battery and the bottles filled to around 80 psi, it started to look a little more promising. So I think I need to tune the gyro values up a little bit more, because at the lower pressures it does start to lose control. Let's just try that again with the tanks relatively empty. Yeah, it just has no control at the lower pressures. The only way to get the bottles filled to 100 psi was to connect it straight to the compressor. Okay, this is the first test at 100 psi bottle pressure. Now I know it's a bit disappointing that the noise from the main lift propellers are louder than the gas thrusters, but there's not much I can do about that. So just imagine it sounds like this. Don't know about you, but I'd call that a pretty good success. The motors are a bit toasty, and so they don't melt through the 3D printed mount, I should probably end the testing there for now. I honestly am so happy with that. If you'd like to learn more about how high pressure gas flowing through a nozzle causes this drone to move through the air, or how a rocket accelerates into space, the most effective way to learn is by doing, which is the reasoning behind carrying out this project. But a far simpler method of learning is to challenge yourself with interactive content. Brilliant challenges you to solve problems, to broaden your understanding of various topics. They have a wide range of interactive courses, from basic forces and acceleration to real-world challenges, such as finding out the correct size battery for your drone. Each course contains clear diagrams and animations to help you learn your way to becoming an engineer. To support these projects and learn more, go to brilliant.org/Tom Stanton and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription. So there we have it, a drone controlled by gas thrusters. I'm really happy with the way it performed in the end. I honestly didn't think it would even fly. So the fact we got a good 10-second hover or so was really good. You may wonder why there's these huge tubes on it now and the massive arms, and that's because I actually wanted to test whether longer arms would give the thrusters a bit more authority to keep it under control. And this worked well at the lower pressures, but when I put it up to 100 psi, it then didn't fly too well. This resulted in it crashing and breaking one of the arm mounts, so the drone needs some repairs doing to it. I'm not sure exactly how we could tackle the issue of the pressure changing so much throughout the flight, because I guess theoretically when the pressure halves, so does the thrust, which then means you need to double the gyro sensitivities, or maybe even at those pressures it doesn't have enough thrust to control the drone. I'm sure it can be fixed on a newer version, but I think this is the best that this drone will fly. I'd like to thank you very much for watching this video. I hope you enjoyed this project, and if you did, then it'd be great if you could leave a thumbs up on this video. If you're new to my channel and want to see more videos such as this, then please click subscribe down below, and a huge thanks to all of my patrons for supporting my channel and letting me try crazy projects like this. Now I believe the sun is just about to set, so good timing to wrap up this video. Thanks once again for watching, and I'll see you in the next video. Goodbye.